Hello, this is Matt Dean with A Plus College Ready, and today we're going to talk about circuits. We'll start with the most simple circuits, which are series circuits. In a series circuit, each device is connected in a manner such that there's only one pathway, or we might call that a loop, by which the charge can traverse through the circuit. Each charge passing through the loop of the external circuit passes through each resistor in a consecutive order. There's some rules that you need to be familiar with series circuits. The potential difference of the source, or the voltage drop across the battery, we might call it, is equal to the sum of the potential differences across each resistor or load. We might write that this way. The equivalent or total resistance is the sum of the resistances of each of the resistors. We simply add up the resistance of each resistor to get the total or equivalent resistance. The current is the same through all parts of the circuit. There's only one way for the current to go. It has to follow that path. As additional resistors are added to the circuit, the total or equivalent resistance increases. And if any part of the circuit were to burn out, let's say one of the resistors was to burn out, the whole circuit will go off because now there's not a complete pathway for the charge to travel through. All right, let's look at a series circuit problem. Here's an example series circuit. So here we're looking at a battery, resistor number 1 and resistor number 2. So this tells us that assume the potential difference across the battery is 12 volts. Resistor 1 is 2 ohms of resistance, and resistor 2 is 4 ohms of resistance. So the first thing it asks us to find is the total or the equivalent resistance. Remember that in a series circuit, to find that, you simply add up the resistance of each resistor. So 2 plus 4. So we have a total resistance of 6 ohms. To find the total current in the battery, we're going to use Ohm's law. Ohm's law is I equals V over R. So we're going to take the battery voltage, the source potential difference, 12 volts. We're going to divide that by the equivalent resistance of 6 ohms. And we're going to end up with a total current of 2 amps. So we're going to think about conventional current. The current's going to leave the positive terminal of the battery, which is the long line. It's going to travel through resistor 1, through resistor 2, and then back to the negative terminal of the battery. The current, since there's only one path, is the same through all parts of the circuit, which means if the total current is 2, the current through resistor number 1 is also 2 amps. Current through resistor 2 is also 2 amps. To find the voltage drop across the resistors, we're going to go back to Ohm's law. This time though, we're going to simplify it for V, voltage drop. V equals IR. So we're going to multiply the current through resistor 1, 2 amps, times the resistance at resistor 1, 2 ohms. And we're going to end up with a voltage drop or potential difference across R1 of 4 volts. We'll do the same thing for R2. The current through R2 is still the 2 amps. The resistance across R2 is 4 ohms, which means the voltage drop across R2 is 8 volts. Notice that if we sum up the voltage drop across the two resistors, 8 plus 4, that gives us the voltage drop across the battery of 12. The last thing we're asked to find here is the power dissipated at R1. There's a couple of ways we can calculate power. We can go P equals VI. We also could go P equals I squared times R. Either way, you're going to get the same answer. I'm just going to use V times I. So at resistor 1, the voltage drop was 4 volts, and the current was 2 amps. So at resistor 1, we'll call it P1, 4 volts times 2 amps. A volt times an amp is a watt. So we're going to get 8 watts. And then at resistor number 2, same thing, P equals VI. So the voltage drop at resistor 2 was 8 volts. The current through resistor 2 was 2 amps. So 8 volts times 2 amps, we have 16 watts going through resistor 2. If these were light bulbs instead of just plain old resistors, light bulb 2 would be brighter. Because to compare the brightness of light bulbs, compare the power dissipated. More power dissipated is going to mean a brighter bulb in most cases. All right, let's move on to the next type of circuit, and these are parallel circuits. In a parallel circuit, each device is placed on in a separate branch. What this means is there's going to be multiple loops, multiple pathways that the current can go through. There's some rules that apply to parallel circuits that are important. The potential difference or voltage drop across each branch of a parallel circuit is equal to the source voltage or the potential difference across the battery. The total current is equal to the sum of the currents through each branch of the circuit. You find the equivalent or total resistance a little bit differently than you did in series circuits. We're going to use this equation. 1 over the total is equal to 1 over the first resistor plus 1 over the second plus 1 over the third, and so on and so forth. As additional branches or resistors are added to the circuit, the total or equivalent resistance of the circuit actually decreases. It's adding multiple paths, new paths. So let's look at an example of how a parallel circuit might work. Notice that we have a battery, and the problem tells us our voltage drop across that battery, our potential difference is 12 volts. Resistor number 1 is 4 ohms. Resistor number 2 is 12 ohms. And we're wanting to find the total or equivalent resistance first. Remember, we're going to use 1 over the total equals 1 over the first resistor, 4, plus 1 over the second resistor, 12. We get a common denominator of 12. 1/4 is 3/12. So let's replace that. Let's add those together to get 4 over 12. So 1 over the total equals 4 over 12. Well, we're not looking for 1 over the total. We're looking for the total resistance. So we need to flip both sides of our equation and get that the total is equal to 12 over 4 or 3 ohms. So that's our equivalent resistance, 3 ohms. Notice that the equivalent resistance is actually less than the resistance of either resistor. To find the total current, we're going to go back and use Ohm's law. I equals V over R. So we'll take the battery voltage, 12 volts. We'll divide that by the total or equivalent resistance of 3 ohms. So that's going to end up giving us 4 amps of current. Those 4 amps of current are going to leave the positive terminal. They're going to get to right here. And at this junction, the current is going to split. Most of it is going to go through this branch because this is the branch with the least resistance. Some of it, though, will go through this branch. To calculate how much goes down each branch, we're going to have to think about the voltage at each one of these resistors. Remember, we said in our video a second ago that in a parallel circuit, the voltage drop across each branch, so here's a branch and here's a branch, is equal to the voltage drop across the battery. Well, since there's only one resistor on each of the two branches, that means the voltage drop across each of those resistors is also 12 volts. So the voltage drop across R1, 12 volts. The voltage drop across R2 is 12 volts. And now to go back and find the currents, we'll go back to Ohm's law. Let's find the current through resistor 1. It's V over R. The voltage drop across resistor number 1 is 12 volts. And the resistance at resistor number 1 is 4 ohms. Well, that means that the current through resistor 1 is 3 amps. At resistor 2, same thing, I equals V over R. The voltage was 12 volts. The resistance at resistor 1 is 12 ohms. So that gives us 1 amp. Notice that in a parallel circuit, the currents through each of the branches have to sum together to be the total current. All right, the last thing we're asked to find is the power dissipated. So again, we can use P equals VI or P equals I squared R. In this case, I'm going to use P equals I squared R. So at resistor number 1, the current was 3 amps. We had to square that. The resistance at resistor number 1 was 4 ohms. So we're going to have 3 squared 9 times 4 to get 36. 36, remember power is measured in watts. So 36 watts at resistor 1. And at resistor 2, again we'll use I squared times R. The current through resistor number 2 was 1 amp squared times the resistance, 12 ohms. So the power through resistor number 2, or the power dissipated at resistor 2, is going to be 12 watts. That's it for a parallel circuit. Now the final type of circuit that you need to be familiar with is called a mixed circuit, or you might also hear it called a combination circuit. So these are circuits that are combinations of series and parallel circuits. They might also be called compound circuits, so mixed, combination, or compound circuits. In order to find the total resistance of such circuits, you're first going to calculate the equivalent resistance of all the parallel resistors. You're then going to treat that entire parallel section of the circuit as if it were one series resistor. You're then going to use the series rules, which means you're going to add that parallel portion to the resistance of each of the series resistors to get the total resistance. And we'll see some problems for that on the next slide. So here's a combination circuit. We're told that the battery voltage is 12 volts. The resistance of R1 is 3 ohms. The resistance of R2 is 4 ohms. And the resistance of R3 is 12 ohms. First of all, we want to find the resistance of the parallel portion of the circuit. Remember, to do that, we're going to say 1 over the parallel resistance is equal to 1 over the first parallel resistor plus 1 over the second parallel resistor. We're going to get a common denominator of 12. So we get 3/12 plus 1/12. So 1 over RP is equal to 4 over 12. We've got to flip both sides of this equation. So RP is equal to 12 over 4, or 3 ohms. Now we're going to think of this whole parallel part of the circuit as if it were one series resistor. So this whole part, we're going to think of it as if it were one series resistor with a resistance of 3. So remember, in series, to find the total resistance, we simply add up the resistances of each resistor. So we've got 3 plus 3 to get an equivalent resistance of 6 ohms. To find the total current, we'll go back to Ohm's law. I equals V over R. We'll use the battery voltage over the total or equivalent resistance of 6 ohms. So we end up with a current of 2 amps. Now, that current leaves the positive terminal of the battery. All of it has to go through resistor 1. There's no other way to go. So the current through R1 is all the current, 2 amps. But when the current gets to this junction right here, some of it splits. Most of it's going to go this way because this is the path of least resistance. Some of it, though, will go this way. And then back at this junction, those currents will come back together so that we have 2 amps of current going through this part of the circuit, 2 amps returning to the negative terminal of the battery. To find the current through R2 and R3, the first thing that we're probably going to want to do is to find the voltage drop across the parallel part of the circuit. So again, we're going to think of this as one series resistor with a resistance of 3 ohms. All the current goes through that parallel part of the circuit. So if we want to calculate the voltage of the parallel part of the circuit, the voltage drop, we're going to take the total current through the parallel part of the circuit, which is all of it, 2 amps, times the resistance of the entire parallel part of the circuit. 3 ohms. So we're using V equals IR. So that gives us 6 volts. That's the voltage drop across the whole parallel part of the circuit. But remember that in parallel, the voltage drop across the whole thing is also equivalent to the voltage drop across each branch. And in this case, since there's only one resistor on each branch, that's also the voltage drop of each of those resistors. So R2 voltage drop and R3 voltage drop are both 6 volts. Now that we have the voltage drops, we can find the currents through each of those branches. So to find the currents, we'll go back to Ohm's law. The voltage drop across resistor number 2 was 6 volts. And the resistance of resistor number 2, 4 ohms. We're using I equals V over R, by the way. So 6 divided by 4 is going to give us a current through R2 of 1.5. 1.5 amps. Through R3, same thing. I3 is going to equal the voltage drop, 6 volts, divided by the resistance of that resistor, which was 12 ohms, to give us half of an amp. Notice that the current through R2 and the current through R3, those add together to be the total current of 2 amps. Now we need to find the voltage drop across R1. To find that voltage drop across R1, just use Ohm's law. V equals IR. The current through R1 was 2 amps, and the resistance of R1 was 3 ohms, which means the voltage drop across R1 was 6 volts. Finally, we need to find the power dissipated at each of those resistors. Remember, power is P equals VI, or P equals I squared R. Here I'm going to use VI. So at resistor 1, voltage drop was 6 volts. Current through resistor 1 was 2 amps. So we get a power dissipated of 12 watts. At resistor 2, same thing. The voltage drop was 6 volts. The current through resistor number 2 was 1.5 amps. Which means the power dissipated at resistor 1 is going to be 9 watts. And finally, at number 3, same thing, 6 volts is the voltage drop. The current was half an amp. So we end up with 3 watts of power dissipated. So if these resistors were light bulbs, light bulb number 1 would be the brightest, then light bulb 2, and light bulb 3 would be the dimmest. More power dissipated means brighter light bulbs. All right, we already mentioned this next point on the previous couple slides. Oftentimes you're going to be asked to compare the brightness of light bulbs. Here we're talking about probably incandescent light bulbs. Compare the power dissipated at each of the bulbs. More power means more energy converted to light, which means a brighter bulb. So let's look at an example problem or two. So here it says assume that elements A, B, and C are identical incandescent light bulbs hooked up in the illustrated power to a 12-volt battery. Which bulb is the brightest and why? Well, the easiest way to think about the bulb brightness is use the formula P equals I squared R. We know that all these bulbs, this one, and this one, all have identical resistances. They're identical light bulbs. So the R is not going to be a factor. So really, to compare the power dissipated, we need to look at the current. Well, this is a mixed or combination circuit. The current leaves the positive terminal of the battery. All the current goes through resistor A. But when that current gets to this junction, some of it, half of it, in this case, is going to go this way, and half is going to go this way. And I know it's half because they're identical bulbs and they have identical resistances. So what that tells me is that all the current goes through A. but only half goes through B and C. That means that bulb A has to be the brightest because it's going to have much more power dissipated. Bulbs B and C will be dimmer, but they will have equal brightness to each other. Another question. Assume that bulbs A, B, and C are identical incandescent light bulbs hooked up in the illustrated power to a 12-volt battery. What happens to the brightness of bulbs A and C if bulb B is unscrewed from its socket? How does the brightness of bulb A compare to the brightness of bulb C? All right, so we're starting out with a mixed circuit, but now this bulb is removed. So now when the current leaves the positive terminal of the battery, it all goes through A. This branch is broken right here, so no current can go through here, which means all of it has to go through C, and all has to go back to the negative terminal of the battery. Again, use P equals I squared R to guide your thinking. All the current goes through A, all the current goes through C. They're identical bulbs. They have identical resistances. Well, that tells you that the power dissipated at the two is going to be the same. So that means that A is going to have equal brightness to C. Now, the other thing we want to know, what happens to the brightnesses of the two bulbs? And there's several ways we could think about that. The first thing, we had a parallel portion of the circuit. Remember that when you add parallel branches, you actually decrease the total or equivalent resistance. So when we take away a branch, that means that our total resistance of our circuit, our equivalent resistance, is going to increase. So the circuit without B has more resistance than the circuit with B. Remember that I equals V over R. So without B, R is bigger, which means that the current is going to be smaller. Well, that tells you that bulb A, since it's going to have less current without bulb B in the circuit than it did with it in there, it's going to get dimmer. So A is going to get dimmer. On the other hand, with C, when B was there, all the current didn't go through C. Part of it went through B. So even though there's a little bit less current, now all the current goes through C, which means C is going to get brighter than it was before. And at this point, the brightness of A and the brightness of C are going to be the same because all the current goes through both resistors. So A is going to get dimmer because the total resistance of the circuit increases when we remove branch B. C is going to get brighter when we remove B because now all the current from the circuit has to go through C, whereas before only half of it did. So another thing we want to talk about is internal resistance. There's some resistance within a battery. We talk about the EMF, or the electromotive force. That's the ideal voltage. The EMF doesn't take into account the internal resistance. The voltage drop across a battery we can find using V equals IR. It's just Ohm's law. But notice that we use that little r to indicate its internal resistance inside the battery. So let's look at how an example problem for internal resistance might look. So it says if a 20-volt EMF battery with an internal resistance of 2 ohms is hooked in series with a 5 ohm and a 3 ohm resistor, how much current flows through the circuit, and what is the terminal or effective voltage of the battery? So first of all, let's draw this out. So when there's internal resistance, oftentimes you'll see a box around the battery and a little resistor symbol. So we have a 20-volt EMF battery. This internal resistance right here is 2 ohms. One of these resistors is 5 ohms, and the other is 3 ohms. Well, this is a series circuit. To find the total resistance, you simply add up the resistance of each resistor, including the internal resistance. So 5 plus 3 plus 2, we end up with a total resistance of 10 ohms. To find the current that flows through the circuit, use Ohm's law. I equals V, so we'll use the EMF, 20 volts, divided by the total resistance. We're using V over R. So we end up with 2 amps of current flowing through the circuit. Now, if the battery is not hooked up to the circuit and we touch a voltmeter to the two terminals of the battery, it's going to read 20 volts. But when we hook up the battery to the circuit and we turn it on, and now we touch the voltmeter to the 2 terminals of the battery, we're not going to read 20 volts because the voltage drops across the battery due to the internal resistance. So first of all, we want to calculate the voltage drop across the battery. And remember, we're going to use V equals IR. So 2 amps of current go across the battery. The battery has an internal resistance of 2 ohms, which means the voltage across the battery drops by 4 volts. So this part of the question says, what is the terminal or effective voltage of the battery? Well, it was rated at 20 volts, but when the circuit's on, it drops 4, which tells us that the terminal or effective voltage is actually 16 volts. That's what we would read if we touched the voltmeter to each terminal of the battery when the circuit was turned on. All right, we also want to talk about what are called Kerckhoffs rules. These are for multi-loop circuits, typically. Most of the time you're going to use these when you can't determine if a circuit is parallel or series, and it's kind of a complicated circuit. The first rule is called the junction rule, and it says that the total current entering a junction must be equal to the total current leaving the junction. The junction rule is simply a restatement of the law of conservation of charge. You can't create charge. You can't destroy charge. It's always going to be there. Rule 2 is the loop rule. And it says that the sum of the potential rises and drops across a loop of a circuit must be equal to 0. The loop rule is essentially another way of stating the law of conservation of energy. So there's some rules for using Kerckhoffs, for applying Kerckhoffs rules. If you're passing through a circuit and you pass through a battery from the negative terminal to the positive terminal, the potential rises. If, on the other hand, you pass through a battery from the positive terminal toward the negative terminal, the potential drops. If you pass through a resistor against the direction of the normal conventional current flow, the potential rises. And if you pass through a resistor in the direction of normal conventional current flow, the potential drops. So let's look at some examples of how this might be applied. All right, so here we have a multi-loop circuit. The blue labels are the loops. So we have loop A and loop B. The red labels are currents. They're labeled with I's. The J labels are the junctions. So we have a junction right here and a junction right here. We want to use Kerckhoffs' loop rule to describe the total potential difference for loop B. Now you can start anywhere in the circuit you want to. I'm going to start right here. And I'm going to move in this direction around my circuit. You can go either way you want to. But as I go through a circuit, notice that the current through this resistor is going in this direction. Remember that when you move through a resistor in the direction of current, the voltage drops, the potential drops. So remember, V equals IR. So through this resistor, the 200 ohm resistor, if I want to know the voltage drop, I'm going to take the current through there, which is I1, times the resistance, 200 ohms, and it's a drop. So I'm going to use a negative to do that. I'm going to continue around the circuit going this way, and I'm going to go up through this resistor. All right, so in this case, the current is I2 and it's going this way, but I'm moving this way through the circuit. So I'm going opposite of the current flow, which means there's going to be an increase in potential. So plus the current through there, I2, times the resistance of that particular resistor, which is 100 ohms. All right, then I'm going to continue around my circuit, and I'm going to go through my battery from positive to negative. When you move from positive to negative, the potential decreases through the battery, so minus 9 volts. I've been through all my circuit elements, so all this has to add up to be equal to 0. So that's applying Kerckhoffs' loop rule to this particular circuit. All right, so now the second question. This time we want to use Kerckhoffs' loop rule to describe the total potential difference for loop A. So I'm going to start, let's just say I start right here. And I move through my circuit. I go through this resistor in the direction of the current flow, which means the potential is going to drop. So we're going to go negative I2 times the resistance there, 100 ohms. We're going to continue around loop A. This time we're going to go from the negative terminal to the positive terminal. When that happens, there's an increase in potential, so plus the battery voltage. And those are the only two circuit elements in this resistor, or in this loop, so those have to sum up to be 0. All right, now we're working with the same circuit, multi-loop circuit. We're asked to use Kerckhoffs' junction rule to describe the currents which enter and leave junction number 1. Well, here's junction number 1. And remember, the junction rule simply says that the currents that enter a junction must be equal to the sum of the currents that exit the junction. So we have coming into this circuit, into this junction, junction 1, we have coming in I0. So I0 is going to have to equal to the sum of the currents leaving the junction. Well, coming out of the junction, we have I1 going this way and I2 going this way. That's it. That's using Kerckhoffs' junction rule to describe the currents which enter and leave a junction. In this case, junction 1. And remember that the junction rule is a restatement of the law of conservation of charge. All right, here's number 4. This time we want to use the junction rule to describe the currents which enter and leave junction 2. Well, we have coming into junction 2, I1 and I2. So I1's coming in, I2's coming in, and coming out is I0. So I1 plus I2 equal I0. And again, that's using Kerckhoffs' junction rule to describe the currents which enter and leave junction number 2. All right, finally, use our work from questions 1 through 4 to help solve for I0, I1, and I2. All right, so I've written down up at the top of the screen our 3 equations that we derived in the previous problem. Up here we have our junction rule. Here's the potential differences for loop A and the potential differences for loop B. Now drop the units just to make the algebra a little bit easier. We're asked here to find the currents. So to find those currents, we're going to first of all take these bottom 2 equations, and we need to solve one of them for a variable because we have 2 unknowns. So I'm going to take this equation and I'm going to solve it for I2. To do that, that's going to give me negative 100. I'm going to write it this way. I2 plus 1.5 equals 0. So I'm just going to add the negative 100 I2 to both sides. So that gives me 1.5 equals 100 times I2. I'm going to divide both sides by 100. And I want to write it up here. I2 is going to be equal to 0.015. And that's going to be in terms of amps. Now I'm going to take the other equation. This one. and write it out. Negative 9 minus I1 times 200 plus I2. I want to go ahead and substitute in the I2. 0.015 amps. Let's just leave off the units again. Times 100 equals 0. All right, simplified down a bit. It's going to be negative 9 minus 200 I1 plus, go ahead and multiply 0.015 times 100. So that's going to give us plus 1.5 equals 0. Now we want to solve that out. We want to solve it for I1. And the easiest way to do that, let's go ahead and combine the 9 and the 1.5. That's going to give us negative 7.5. Now let's add the 7.5 to both sides. And then let's divide both sides by 200. When we do that, I1 comes up to be negative 0.375. 0.0375 amps. Now, you can't really have a negative current. The negative current tells us that the direction that we have marked for I1 in our circuit is just the wrong direction. So instead of going this way, I1 is actually going this way. So we got the direction wrong. So I1 is 0.0375. Now we do want to keep using that negative sign while we're finding I0. Remember that I0 is the sum of I1 plus I2. So I0 is going to equal negative 0.0375 plus 0.015. Sum those up. I0 is equal to negative 0.0225 amps. And again, the negative tells us that we had the current marked in the wrong direction. All right, that's it for our Kerckhoffs rules. Hope that helped.